Last part is weak convergence and bounded linear transformations. Weak convergence. Is the screen visible to you? Screen visible आहे का?
Yes.
Yes, ma'am.
Okay, good. Weak convergence. A sequence xn n is equal to 1 to infinity. In a non-linear space, it's said to be weakly convergent, or we can say xn converges weakly to x. If there is an element x belongs to capital X, such that for every functional f belongs to x dash is dual space of X. It contains bounded linear functionals on X. For every such f, we have f of xn converges to f of x as n tends to infinity. We write xn converges weakly to x in this way as given in this bracket. We repeat, let xn be a sequence in non-linear space capital X. Then we say xn is convergent to x weakly. Xn converges to x weakly. That is, in this way we write, if for every x if there exists an element x belongs to capital X such that xn converges to x weakly if and only if f of xn converges to f of x as n tends to infinity. F for every functional f belongs to x dash. Mod of f of xn minus f of x tends to 0 as n tends to infinity. Or we can write limit n tends to infinity f of xn is equal to f of x. And x is called as weak limit of xn, sequence xn. Next we see strong convergence. Let xn be any sequence in non-linear space capital X. We say xn converges to x strongly, or xn is strongly convergent to x if there is an element x belongs to capital X where the sequence is converges. Norm of xn minus x tends to 0 as n tends to infinity. That is, limit n tends to infinity, norm of xn minus x is equal to 0. Then we say xn tends to x, written in this bracket, as n tends to infinity. We don't write here W upon the arrow because this is strong convergence. X is called a strong limit of sequence Xn, and we say that sequence Xn converges strongly to X. Theorem. Also, there is a note. Okay. Theorem. Let Xn be weakly convergent sequence in a norm-linear space. Then number 1, the weak limit of sequence Xn is unique. 3 parts are to prove. Number 2, the sequence norm of Gx n is equal to 1 to infinity is bounded in R. Here it is norm of Xn n is equal to 1 to infinity outside the bracket to right is bounded in R. In place of g of x, it is xn. Every subsequence of xn n is equal to 1 to infinity converges weakly to x. Or converges weakly in capital X, where capital X is the norm linear space. Proof. Let Xn be arbitrary arbitrary sequence in norm linear space capital X, and Xn converges to X weakly in capital X. Don't write here convergent, arbitrary convergent sequence, because it is weakly convergent in norm linear space capital X. Limit n tends to infinity f of xn is equal to f of x by definition of weakly convergent sequence for every f belongs to x dash. X dash is dual space of x. Suppose that xn converges to y belongs to capital X. Therefore, xn converges weakly to y. It is y. We have taken y. And also, upon arrow, you can write here w, which states that xn converges to y weakly. So limit n tends to infinity f of xn is equal to f of y. Give this equation number b. We are proving that the limit is unique. So we take another limit y and prove that x is equal to y. From a and b, limit f of x minus y. You have to take here f of x minus y is equal to f of x minus f of y. Or by this way also we can write limit n tends to infinity f of xn is equal to limit n tends to infinity f of xn. So f of x is equal to f of y. F of x minus f of y is equal to 0. So f of x minus y is equal to 0 because f is linear. F belongs to x dash and x dash contains bounded linear functions. So f of x minus y is equal to 0. Hence x minus y is equal to 0. Thus, x minus 5 is equal to 0 and therefore x is equal to y. Second part, let sequence f of xn be convergent sequence of number. So sequence f of xn is bounded because every convergent sequence is bounded. This is theorem in real. In general. So mod of f of xn less than or equal to cf, c to the lower suffix f. C to the lower suffix f is any constant. If sequence is bounded, then absolute value of every element will be less than some constant element. Now we define a canonical mapping C from x to x double dash. X double dash is second dual space. We have seen the definition of second dual space. Let us repeat. Let X is linear vector space and X dash is its dual. Then algebraic conjugate of dual X star. Algebraic conjugate of algebraic dual X star, denoted by X double star. It's called second dual. Canonical mapping. For each x element x belongs to capital X, there exists an operator C such that C from x to x double star is called a canonical mapping of x into x double star. Let X be a vector space and X star be its dual and X double star be its second dual. Then the canonical mapping C from X to X double star given by C of X is equal to Gx. This is not G of X, it is Gx, where Gx of F is an element in X star, is equal to F of X. If range of C is equal to X double star, then vector space is said to be algebraically reflexive. Algebraic dual space, the set of all linear functional on a vector space X over scalar field K is called as an algebraic dual space of the vector space X. We define a canonical mapping C from X to X double dash such that Gxn of F is equal to F of xn. It is not G of xn of F, it is Gxn of F. Xn is lower suffix. Is equal to F of xn for all of F belongs to X star, or we can say X dash. In place of X star, we write here X dash. X dash is dual of X. And Gxn, these are also functionals which belongs to X double dash. These are functionals on the space of functionals, that is dual of dual. As X dash is dual of X, X double dash is dual of X dash. and it is defined as gxn of f is equal to f of xn. And f of xn, this value will belong to scalar field. So G is functional. Thus, mod of gxn of f is equal to mod of f of xn for every n. And this is less than or equal to Cf. You can write here Cf or C to the lower suffix f also. Because we have shown that for every n, mod of f of xn is less than or equal to some constant. Because f of xn is a convergent sequence, so it is bounded. So mod of f of xn less than or equal to some constant Cf. Hence, gxn of f, this is a sequence. Sequence n is equal to 1 to infinity over sequence over n is bounded for every f belongs to x dash. Gxn will be the functional whose domain is x dash. So gxn of f sequence n is equal to 1 to infinity is bounded. Therefore, norm of gxn n is equal to 1 to infinity is bounded in R. In some books, in this theorem, we have given that as we prove norm of gxn sequence, you have to write here bracket because this is a sequence. Sequence norm of gxn is bounded. Also, we have to prove that sequence norm of xn is bounded. If it is asked to prove, then 2 steps to add. And the next step will be to apply the uniform boundedness theorem, which is in 3rd chapter. Okay, we don't take that part because in notes only first part is given. So we learn only first part. That is sequence of norm of gxn n is equal to 1 to infinity is bounded. You have to write here bracket to norm of gxn because this is sequence of norms of gxn. G to the lower suffix xn. Part 3. To prove that every subsequence of xn, sequence xn I is equal to 1 to infinity, converges weakly to x. That is to prove f of x and k converges to f of x. If xn converges to x, it means that f of xn converges to f of x by definition of weak convergence. But we are proving that every subsequence of sequence xn converges weakly to x. That is to prove f of x and k converges to f of x. Here x to the lower suffix nk. This is by definition of weak convergence. We have to prove this. let xn converges to x weakly in capital X. Because we have given in theorem that xn be a weakly convergent sequence. So we suppose as it is weakly convergent, it converges to an element x in every part of theorem. So sequence xn converges to x weakly in capital X. Therefore, the sequence f of xn n is equal to 1 to infinity converges to f of x in K, because images of xn under F will lie in scalar field. For every F belongs to x dash is dual of x. Xn converges to x weakly in nonlinear space X, so f of xn converges to f of x in K. For every F belongs to x dash. Limit n tends to infinity, f of xn is equal to f of x. But f of xn being a sequence of numbers, image of xn under F will belong to scalar field. It belongs to scalar field because F is a functional. And so sequence f of xn being a sequence of numbers, being a sequence of scalars, and scalar field is R or C, and it is complete. That is, every sequence has a convergent subsequence. Sorry, being a sequence of numbers. So every subsequence f of xn converges. Yes, correct. So every subsequence of f of xn converges and converges to some limit f of x. By definition, I will tell you later if the field is compact or some other basis it is given. So f of xn converges to some limit f of x. Hence limit n tends to infinity f of xn k is equal to f of x is equal to limit n tends to infinity f of xn. Hence xn k converges to x weakly. As n tends to infinity, but xn k be arbitrary subsequence of xn. So every subsequence of xn converges weakly to x. Only we use the definition of weakly convergence and thus it is proved. तुम्हाला आतापर्यंत जितकं झालंय त्यामध्ये काही प्रॉब्लेम आहे का? तुम्हाला ज्या नोट्स दिल्या त्या तुम्ही लिहिल्या का?
हो मॅम.
लिहिल्या? काही प्रॉब्लेम आहे? Any problem? यासोबतच मी तुम्हाला रेकॉर्डिंग पण देतच आहे प्रत्येक लेक्चरची सो दॅट ते ऐका. So that you will understand. हा चॅप्टर आता संपत आहे. एक थेरम राहिलाय. नेक्स्ट फक्त आपण थेरम लिहून घेऊ, बिकॉज मीटिंगला फक्त 6 मिनिट बाकी आहे. नंतर मीटिंग ऑटोमॅटिक स्टॉप होऊन जाईल. सो दॅट आपण थेरम लिहून घेऊ. प्रूफ मे बी वी सी इन नेक्स्ट लेक्चर. नेक्स्ट थेरम इज let n is equal to 1 to infinity be a sequence in non-linear space. Then show that strong convergence implies weak convergence with the same limit. If xn converges to x strongly, then it converges to x weakly also. Number 2, the converse of part 1 is not generally true. That is, if a sequence xn converges to x weakly, it do not imply that it converges to x strongly. Number 3, if dimension of capital X, that is non-linear space capital X, is less than infinity, then weak convergence implies strong convergence. That is, if X is finite dimensional, then weak convergence implies strong convergence. In part A, we have given strong convergence implies weak convergence. In part 2, we have to show generally the converse is not true. But in part 3, we show if X is finite dimensional, then the converse also true. Those students who need the lecture should join on time. Time वर join होत चला ज्यांना lectures ची आवश्यकता आहे. Is it clear? Yesterday's theorem clear to all? कालचा theorem सगळ्यांना clear झाला का? Any difficulty up to here? तुम्ही response करत चला.
No, ma'am.
काय नाही समजलं त्यातलं?
समजला म्हणजे
ठीक आहे. हा चॅप्टर इथे संपणार आहे. हा लास्ट थेरम झाला की नेक्स्ट चॅप्टर आपण थर्ड किंवा फोर्थ सुरू करू. Okay, we stop here and we meet tomorrow.
Hello, madam.
Yes, yes. Yes.
ऑप्शनल मध्ये कोणते कोणते सब्जेक्ट चूज करायचे आम्ही, म्हणजे विदाउट थेअरीचे? हॅलो.
Yes.
आवाज नाही लागला.
I will ask in college and will tell you tomorrow.
ओके मॅम. आणि एक्झाम ऑनलाईनच होणार आहे का ऑफलाईन?
It can't be told now. We are not informed. But MCQ pattern may be.
Okay, thank you.
Okay. So we meet tomorrow.
Yes, ma'am.